pros and cons of each type of spray nozzle, and then some suggestions on when to use them and what situations to use them. So let's start with simple hydraulic nozzles. This is the most basic type of nozzle. We have a cleverly shaped bit of metal or plastic with a pressure fluid supply to it, and that produces spray. Now the advantages of this, the pros are, they're very, very simple. There's nothing really to go wrong in them. They have a very low capex, so the cheapest type of spray nozzle, and they have a low running cost. We've just got the pumping costs there. The disadvantages in gas quench systems is we need high pressures to generate small droplets, and small droplets are good in gas quench systems because they'll exchange heat a lot quicker, they'll absorb heat a lot quicker, so they'll act a lot faster. But we need high pressures in hydraulic nozzles to get the drop size down. And we've got very low levels of control. We've only got one variable, we've got the pressures of the nozzle, and that's it. So we've got low levels of control. We can't vary the flow rate too much, and if we do vary the flow rate, we're going to be affecting the drop size quite a lot, because the only thing we can change is that fluid pressure. So when to use them? Well, if you've got enough pressure to deliver a good drop size that's suitable for the heat absorption rates that you need, then they're a perfectly valid choice. And if you have a fairly steady and stable cooling requirement that you're not going to need to vary it an awful lot, if those two criteria are met, then these are a good choice of spray nozzle for gas quench systems. Moving on to spillback nozzles. This is a more advanced type of spray nozzle where we spill back part of the flow. What it gives us is an advantage of being able to vary the flow rate quite considerably. They are a lot more expensive and more complex though. So the pros of a spillback nozzle. The main advantage is we have a high degree of flow rate control. The advantage of the spillback is we can vary that flow rate by a factor of up to 10, so we can turn down rate of up to 10 without greatly affecting the drop size of the spray nozzle. So this allows us to deal with variable heat loads without affecting the heat absorption rate due to the drop size. Disadvantages are they have a high running cost because of the nature of the way that they work. We have to pump the fluid at the highest maximum pressure, and then we're actually siphoning back, spilling back some of that fluid, effectively wasting that energy. So we're basically pumping at a higher pressure than we actually need to. They can be slightly energy efficient. They're more complex than a simple hydraulic nozzle, so there's a bit more to go wrong on them, and they're more complex to install and set up. When should we use spillback nozzles? Well, basically, when you have a highly variable cooling requirements, they're the best nozzle choice in many situations, especially if you can't add air into the system. They're probably the only choice you've got if you've got highly variable cooling requirements. The other choice is air atomizers. Basically introduce air into the fluid stream, and they use that compressed air to atomize the fluid and to get it to go where it needs to go. So they work in a fundamentally different way to spillback and simple hydraulic nozzles. The advantages are they can actually run at very low fluid pressures and produce very small drop sizes even at low fluid pressures. So even at 1 or 2 bar fluid pressure with 2 or 3 bar air pressure, we can get very, very finely atomized sprays. So we can increase that surface area and increase the heat absorption there. We can also achieve quite good turn down rates because we've got air in there as a second variable. We can actually vary the flow rate and keep relatively consistent drop size by the interplay between those two variables, the air pressure and the fluid pressure. We can achieve reasonably good turn down rates, and so we can cope with variable cooling requirements. So what are the disadvantages? Well, they're not suitable for all applications. We are adding air in there, and so some applications we don't want to add any air in there for a variety of reasons. Yes, you could substitute the air for an inert gas, nitrogen or argon or something like that, but that can get expensive. So if you can't really add air into your system for whatever reason, then they're just ruled out, you can't use them. Second disadvantage is they're more complex. I mentioned that interplay between the fluid pressure and the air pressure. That can get quite complicated, so they're a lot more complicated to set up and get running right, and some quite small variations in air and fluid pressure can produce quite big variations in the flow rate and drop size. So we've got to have very, very good control on particularly the air pressure in these systems, so they're more complex to set up and maintain. Because we're using compressed air, they'll be more expensive to run and maintain, so we've got to maintain a compressed air system as well as a fluid delivery system, so they're more expensive to maintain. Just to the nature of the design of the actual nozzle itself, they can be a bit more delicate, although we do have some robust air atomizing nozzles specifically for harsh environments, but typically they can't take quite as much punishment as a spillback or a simple hydraulic nozzle. So when to use air? If air is able to be added, if application allows that, they're always a good option to consider because you can achieve high degrees of control at low pressure, which may be a big advantage. They're worth considering in any situation where air is permissible.